Good afternoon, good evening all students. I am Vinayak Kulkarni. I am from Mechanical Engineering, IIT Guwahati. I am here to discuss about our course Aircraft Propulsion. Till time what we have covered or what we have seen in aircraft propulsion is that what is the basic thermodynamic cycle of aircraft propulsion. We have seen that Brayton cycle governs the aircraft propulsion. Every component of Brayton cycle is dealing with a separate thermodynamic process. In case of aircraft propulsion, Brayton cycle is an open cycle. So we have seen its variants. Its variants like we have seen how a Brayton cycle alone would be without any attachment, and then we have moved towards the attachment like reheat, heat exchanger. We have also seen intercooling. So these things we have seen. We have seen what are the impacts of these attachments on the performance of the cycle. Then we have seen that if we have non-ideal components, then how would be the performance of the Brayton cycle. Then we have moved towards the actual cycle where we have considered that there can be pressure loss in the heat addition process, and hence we would get differential pressure ratios for the compressor and the turbine. Then we are moving next part where we will be talking about, and we are continuing about the aircraft engines like turboprop, turbojet, turbofan. So this was the part which we have till time dealt with. The next part of this course will be dealing with compressors and turbines and cascades. We will see those lectures in that part. So our live session here is basically on the questions and addressing the issues what we were actually unable to understand through the videos. Loudly. One of the questions asked by the student is, what is the optimum pressure ratio? Here in the class we were working with the Brayton cycle, and when we were working with Brayton cycle we tried to calculate the properties, thermodynamic properties of the working medium at all the corners. Basically we know the Brayton cycle. Then if we try to plot the Brayton cycle on TS diagram, then we would get it like this. So we will have 1 to 2 compressor, 2 to 3 heat addition, 3 to 4 combustion, and 4 to 1 heat rejection. Then we were knowing everything at state 1. And since we were knowing everything at state 1, and we would be knowing the maximum cycle temperature at state 3, using these known things we proceeded and found out what are the properties at all the corners. Specifically we tried to find out what is the temperature and what is the pressure at different corners, which are 1, 2, 3, 4. Once we know this, we tried to find out work and heat interaction, and then we moved toward the net work. There we said that W net is equal to Wt minus Wc. Now Here we calculated WT, which is turbine work, and we said that it is equal to Cp into T3 minus T4 minus Cp into T2 minus T1. And then however, we have assumed here that Cp is constant, and then we have calculated T4 and we have calculated T2, and obviously these temperatures are calculated based upon the pressure ratio. So we can replace this T4 and this T2 in terms of pressure ratio. So then we can rewrite W net in terms of pressure ratio, and then we would have some known quantities in this expression, and those known quantities are T1 and T3, which are the constraints for the given W net. So it would turn out from the expression that W net is function of pressure ratio for given T1 and given T3, and then hence we can differentiate this expression, since W net can alter for given T3 and given T1 if we change the pressure ratio. So pressure ratio remains the only variable if T1, T3 and gamma are the constants, and then what would happen is we will get one specific pressure ratio at which W net becomes maximum. If we have pressure ratio more than that, or if we have pressure ratio lower than that, then the W net is having lower value than this optimum pressure ratio. So optimum pressure ratio is the pressure ratio at which W net is maximum. There is one thing to remember, that efficiency is also function of Rp, and efficiency always increases if we increase the Rp. So optimum pressure ratio means the pressure ratio at which the efficiency is, at which the network is maximum. Then we have next question. One of the students has asked that explain about ramjet. Ramjet is a typical aircraft engine. Again, it is of the category of air breathing engine, where we are also taking air into the engine as we take in case of piston cylinder engines or turbojet or turbofan engines. So air remains the usual oxidizer for this case as well. So a typical ramjet engine will be like this. So there will be some intake, so there is a flow which is supersonic, so which has Mach number more than 1. So the ramjet engine has an issue that it is a parasite engine. We have to reach Mach 1 using other engines, and then only ramjet engine can operate. So here combustion will take place in the subsonic speed, however the flight speed is supersonic. So this is flight speed, which is supersonic. Air enters into the combustion chamber in this region, and this combustion chamber, it would have got decelerated to the velocities which are leading to subsonic speeds. So here Mach number is less than 1, and then fuel will be injected, and injected fuel will combust with the high temperature, high pressure air, and then this combustion product would go through a CD nozzle, which is convergent and divergent nozzle, and then we can get the thrust. So ramjet engine, in short, is an engine which takes the air, or which has air at the inlet as supersonic, and which combusts the air in the subsonic speed. So that is what a ramjet engine is. So the question asked was, what is Clausius inequality? Actually, Clausius inequality is the part from the basics of thermodynamics, and it deals with entropy change and heat transfer. So, Clausius inequality says that DES, change in entropy in a process 1 to 2, is always greater than 1 to 2 dq by T for a reversible process, and for any process and for reversible process ds is equal to dq by T. So, this is Clausius inequality, where we actually can find out what is the entropy change, and then that entropy change would be always more than dq by T in that process 1 to 2. This is the expression for Clausius inequality. Actually, this question would have been asked in one more perspective, that in the lecture I was explaining this using PV diagram, and then one of the processes was turning out to have almost horizontal line. So, student is saying that while explaining Clausius inequality, you considered isotherms and adiabats for the process on PV diagram. It should be taken as TS diagram. Actually, this is almost correct, there is no problem. Central idea for this explanation is same, that no two adiabats can intersect with each other. So, that explanation will happen in any chart, whether it is TS diagram or PV diagram. So, no two adiabats should intersect with each other, such that if two adiabats will intersect, we can make one more isotherm intersecting these two, and then we can construct one cycle with 3 processes, where we will have one isotherm and 2 adiabats, and then we can construct a heat engine, and it will violate the second law of thermodynamics, and then such cycle is not possible. However, the diagram with horizontal line will represent isotherm in TS diagram. This part, as said by the student, is correct. In case of PV diagram, we have to remember one more thing, that the isothermal line will have lower slope than the adiabatic line. So, the part which I was explaining in the class should be taken in the perspective that the isothermal line is a line with lower slope than the adiabatic line, and the two adiabats should not intersect with each other, and then that would give us the idea of Clausius inequality. Give details of Carnot cycle. This is a question asked by a student, and then this question actually is again from the lecture where we were talking about the review of thermodynamics, and we are talking about the Carnot cycle. So, Carnot cycle practically for gases it is not possible, since Carnot cycle is comprised of 4 processes, where we have 2 processes as isothermals and 2 processes as adiabatics. So, this will look like a square or rectangle in a TS diagram. So, this is Carnot cycle for all cycles. So, these are 2 isentropic processes, and these are 2 isothermal processes, and these isothermal processes will have heat addition and heat rejections. And this Carnot cycle cannot be operating if gas is the working medium, since process 2 to 3 we have temperature constant and we are having heat addition. We know that gas has the specific heat, and which would lead to Qin is equal to change, heat addition would lead to change in temperature, and then we cannot have Carnot cycle with gases. However, a Carnot cycle can be thought in case if we are having phase change and if we are having a dome. Inside the dome we can have Carnot cycle operating, where we will have this heat addition process is isobaric plus isothermal, heat rejection process is isobaric plus isothermal, and this is basically Rankine cycle inside the dome, and Rankine cycle inside the dome is almost same as the Carnot cycle. There we are practically taking help of isobaric process for heat addition, since phase change takes place at isothermal and isobaric processes. So, next question. In lecture 10 and previous classes, we take one variable as beta. What is beta? I know beta is equal to maximum temperature of the cycle to minimum temperature. In diesel cycle, that beta means cutoff ratio. In Brayton cycle, what is that beta variable? Student has answered here itself that beta is the ratio of maximum temperature of the cycle to minimum temperature of the cycle. We continue with this philosophy for beta, since in our case Brayton cycle beta is T3 by T1. This is the maximum cycle temperature divided by the minimum cycle temperature. Next question is, what is difference between the cyclic process and reversible process? This is a fundamental question from the thermodynamics. Here question is asked about process and the student is trying to compare two processes. We have to understand one point, that there are different processes, and then each process, each category of defining process is different. We can define process first on the basis that whether the process is reversible or irreversible. Then this is one category where we are defining whether the process is reversible or irreversible. In that category, we are trying to find out whether the system can get restored to its original state. If we are having, suppose, one diagram, let us take TS diagram, and then this is a process 1 to 2, and we are drawing it by thick line. By the convention of thermodynamics, that means the process is reversible. That means that if we want to go from 2 to 1 back in the same process, we can get the same states, 1 to same intermediate states, and we can come back to state 1. But if we are going by some other path and we are showing it by dotted line, then it means that process is irreversible, and that means that we don't know which is the intermediate state, and that's why we don't know whether we have come back from 2 to 1 by achieving the same states which are intermediate. So this is a category in which we are trying to see whether system can restore its original state if we try to reverse the process. Now student is trying to compare this with a cyclic process. Cyclic process is a process where system is purposely brought to its original state. So this is 1, and system goes from 1 to say 2, 2 to 3, and then system is brought back to its original state. Now here is system is brought purposely to the original state. Now here the problem is cyclic process need not be reversible. So we might, if at all we do next cycle, then we might not end in having same intermediate state as what we have in the first cycle. So cyclic process need not be reversible, and as what we see in case A here and in case B here. In case A here, we are executing a non-cyclic process. System is brought from 1 to 2, that's all, and we are pretending that if we go back from 2 to 1, then we will trace the same intermediate state. Here in the case B, we are actually coming back to the first state from where we started, and we are saying that since we came back to original state, this is a cyclic process. Here we are not seeing whether we are going to have same intermediate processes in the cycle as what we are doing while going away and while coming in. Cyclic process, as what we see, we have Brayton cycle. While going away from one, we have two processes where we have one is isentropic and other is isobaric. While coming to one, we have again two processes, one is isobaric and other is again isentropic, but both the two processes are different from the initial two processes. So the processes which are telling us to go away from one would be different from the processes which are telling us to come towards the initial state. But when we are talking about reversible process, we don't have option. We are coming back to state 1 in the same process. So in the same non-cyclic process is made reversible. Next question is, what are given? We are given that the nozzle is adiabatic. While finding T2 and P2, why we have used general equation PV is equal to MRT and not PV raised to gamma is equal to constant? This is a fundamental question. Here we have to understand that equation of state, what does it mean and what does it mean by a process equation. PV is equal to MRT is an equation of state. So all the variables here, PV is equal to MRT, means if we are at state 1, then it is P1 V1 is equal to MRT1. If we are at state 2, then it is P2 V2 is equal to MRT2. And if we are at state 3, then it is P3 V3 is equal to MRT3. So this is equation of state. So we are using state variables to be calculated or evaluated or used to find out other state variables in the equation. So as it is said, we know P2 and T2, so we can find out other variables of the state, or we are using other variables of the state to find out P2 or P2 T2. So all the variable, if one of the variables is unknown for the state, then we can use equation of state to find out that variable of that state. However, PV raised to gamma is equal to constant is a process equation. If this equation is written, then it will be written like P1 V1 raised to gamma is equal to P2 V2 raised to gamma. That means if we are trying to use this equation, then we are using all the variables of one state and some variables of the other state, or rather except one variable of the other state, such that by equating this we can find out other variable of that state. Suppose here we know P1, V1 and P2 and we want to find out V2. We can use equation of process. In this case, we suppose know P2, V2 and then we have to find out T2. So if P2, V2 is known and T2 is unknown, we are using equation of state. If P1, V1 is known along with P2 and V2 is unknown, then we are using the equation of process. So this is the difference. Now we will take some questions in this session. So let us interact for the questions. one of the questions asked by the student is axial flow machines experience lesser drag and produce less stage pressure ratio than radial flow machines. Actually, this will be explained in detail in the next classes, but it is for the gist I can explain here. Axial flow machine is like axial compressor or axial turbine, and centrifugal compressor is the radial flow machine. So the drag experienced by the centrifugal compressor is proportional with its diameter. So as we increase the diameter, we experience more drag in case of centrifugal compressor, but the drag is very much less since the flow comes in and the blade is thin. So we will have lesser drag experienced by the axial flow machines, which are axial flow compressors. So the issue is the motion of the flow is arranged in such a way in axial flow machines that there is lesser obstruction for the flow. However, the flow turns in the radial flow machines, it will come axially and it will go radially. So there is obstruction to the flow, so drag experienced by the flow is more in case of radial flow machines, and this will be further more detailed analyzed in the down chapters of compressors. But in this process of compression in axial flow machine, we have a restraint or constraint that the flow in the compressors is experiencing the adverse pressure gradient, and we are having the axial flow machines where the pressure rise is going to take place in the direction of flow. So we have constrained that flow should not separate and flow should not form a separation bubble, which will reduce the mass flow which is going out from the machine. So what would happen is, in this case we have to take this care, so flow is experiencing gradual pressure rise, so the experienced pressure rise by the flow is low in case of axial flow machines. However, in radial flow machines, the centrifugal force is taken for help to raise the pressure, so the pressure rise will be more and more if diameter is more and more. So for a given diameter, centrifugal force will rise the pressure, and that centrifugal effect, since it is rising the pressure and not the diffusion process as what it happens in the axial flow compressors. Axial flow compressors will have the stators, and those stators will diffuse the pressure and diffuse the kinetic energy and make it to pressure rise, and then that is going to happen after one set of rotor blades. We have stator blades, rotor blades, stator blades. One rotor and one stator blade assembly is called as one stage of turbine. So initially we give work input in the rotors, and that work input would be converted and used to rise the pressure in the stators. So that is why the pressure rise has to be gradual. But in case of centrifugal compressor, the centrifugal force will be helping to rise the pressure. So what would happen is, we will have pressure rising at all the sections in the centrifugal compressor, and then we will have, that is why the larger diameter would give you larger pressure rise, but at the same time it would give you larger drag. So this is the difference between the centrifugal compressor and axial compressor, and this is what we mean by the sentence that axial flow machines experience lesser drag, but they would also produce lesser pressure rise. One student has asked the question, what is the difference between the reheater and afterburner? The question here is from the perspective that a reheater actually is there between two turbines, we would have expanded the gas, we would have first heated the gas in the combustion chamber, then the gas will experience the high pressure turbine, it will come out of high pressure turbine, it will again experience heat addition, and then again it will go to the low pressure turbine. So there is reheater placed between two turbines, high pressure turbine and low pressure turbine. So this is what a typical reheater would be. But afterburner would not experience any turbine. Afterburner is also a process of heat addition into the gas at constant pressure. But once you add the heat in the afterburner, then there is no turbine which will be used for the generation of mechanical energy, but the energy which is entered into the flow in the form of combustion energy, that energy will be utilized for the thrust or increasing kinetic energy of the flow. So this is the difference between afterburner and the reheater. आप है ना पीपीटी का फर्स्ट स्लाइड दिखा दीजिए. Okay. Will there be generation of shock? There is a question. It says that will there be generation of shock waves near inlet duct intake process at any stage of operation of aircraft engine? This is a nice question. This question actually we are having dealt in the complete course only for the flows which are having Mach number less than 1. So our complete course will not have dealing with shock waves. In general, whenever we will deal with the intakes of turbojet and turbofan engines or turboprop engines. But if we are talking about ramjet engine, then ramjet engine inherently would have shock waves at the intake. But the examples which we are dealing with in the ramjet, they are simple examples where we will not use the concept of shock wave. Okay, but question is logical. We can experience shock waves at the intake. Intake is a duct for us which is supposed to compress the air. So the process of compression has to be done by the duct. So as nozzle expands the flow, duct will diffuse the flow. Nozzle expand means nozzle will reduce the velocity, reduce the pressure and increase the velocity of the flow. So here in case of the intake, it is a diffuser and it should reduce the velocity and increase the pressure. So that process has to be gradual. But when the flow experiences the shock wave, then that process becomes sudden, and this can happen in case of supersonic flows, and this can happen in case of, prominently this will happen in case of ramjet and scramjet engines, where we will have supersonic flow at the inlet. So the duct's partial job would be done by the shock wave for the rising the pressure. So the pressure rise will be done partially by the shock wave and partially by the intake. But if pressure rise partially is done by the shock wave, then there will be loss in total pressure, which we are not assuming in case of intake. Rather, if at all we assume, that assumption is towards the minor total pressure loss which is due to friction, but it will turn out to be prominent if we are working with the intakes with shock waves. So in our course we till time have not dealt, or we will not deal with intakes with shock waves, but question is logical. Yes, in the intakes, if aircraft engine experience supersonic flow, then they can have shock waves at the intake. The question is, are those attachments to the gas turbines can practically be implemented? Yes, these attachments can be implemented practically. We know there is one thing, that the engines can also be used for production of work, and that can be converted into electrical energy. So, these all attachments we can think to be implemented for the electricity generation also, and in case of aircraft engines also we can implement these attachments, there is no problem. Question is, what is compressor surge? This question is interesting. We are not dealing too much about this surging problem in the course. However, we have touched this problem by considering the losses in the compressor, which are going to come later. Compressor, we are talking about the axial flow compressors in the course mainly, and the problem when we are talking about axial flow compressors, they might experience surging. Surging means the reversal of the flow in the axial flow compressors, the separation of the flow in the axial flow compressors. Actually, there is positive displacement compressor and then there is non-positive displacement compressors. Reciprocating compressors are positive displacement compressors, since the motion of the flow is from the inlet to the outlet. The flow cannot go out from the inlet. But if we are talking about the axial flow compressions, then there is a chance that flow can come out from the inlet. So, from the outlet flow can come in and then it can go out from the inlet. So, this is a problem. That means we are having reversal of the flow somewhere, and this is a point of design, that so only we have to have very small pressure rise of the flow in the direction in which the flow is taking place. So, axial flow compressors are very much prone for the surging, since if rather we are having very high pressure rise in one stage, since flow separation can take place in adverse pressure gradient. Adverse pressure gradient means if in the direction of the flow pressure rises, that is called as adverse pressure gradient. So, such adverse pressure gradient can lead to flow separation, and compressors are inbuilt adverse pressure gradient machines. So, compressors are very much susceptible for the flow separations, and flow separations at worst would lead to surge, where we will have stopping of the operation of the compressor. So, it is very much possible to have surging in a compressor, and that is practically would lead to stopping of a compressor. Thank you for the Teachers' Day wishes. Thank you very much to all students. Question is, what exactly happens if choked flow in the nozzle? We have explained what do we mean by choking. In case of nozzle choking, we are, if I go back, how did we explain choking? Was that for a given inlet conditions to the nozzle. So, nozzle inlet conditions are fixed and they are given, and now we are trying to reduce the outlet pressure or exit pressure to the nozzle. If we try to reduce the exit pressure from the existing pressure, then there will be increased mass flow rate of the flow through the nozzle. At a particular exit pressure of the nozzle, we get maximum mass flow rate. There onwards, if we reduce the exit pressure, then we cannot get the increase in mass flow rate of the nozzle, and that means nozzle is choked. Now, what is happening? Here we should understand that if initially nozzle exit pressure is same as the reservoir pressure of the nozzle, then there is no pressure difference, then there is no mass flow rate, and then there is no velocity anywhere in the nozzle, zero velocity. Now, if we decrease the exit pressure, then there is small pressure difference, and that small pressure difference would lead to small mass flow rate, and there is little velocity. Now, if we keep on decreasing the exit pressures, then the velocity would increase in the nozzle, and what would happen, that nozzle is convergent divergent for us in this explanation, that the convergent section would reach to sonic velocity at the minimum cross section, and this sonic velocity, once it is reached, then divergent section would act as the nozzle, and once the divergent section acts as the nozzle, then the reduction in the pressure in the exit, that information cannot proceed to the upstream towards the reservoir, and reservoir doesn't allow more mass flow to pass through the nozzle. So what would happen is, once the nozzle is choked, the information of decrement in the pressure in the exit or in the exhaust doesn't pass through the reservoir, and reservoir doesn't pass extra mass, and hence mass flow remains choked. So this is a typical characteristic of supersonic flow, that supersonic flow actually will have problem that it doesn't pass the information to the upstream. The flow was subsonic when mass flow rate was not maximum, flow was subsonic, so that is why it was passing the information of downstream towards the upstream, and that is why more mass was coming into the nozzle. Okay, what kind of engines or propulsive systems are used in the missiles? Missiles most commonly use the rocket engines, which are non-air breathing engines sometimes, and sometimes they can use the ramjets, but initially they are to be propelled by aircraft engines. So we might see that missiles are placed beneath the aircraft wings. So aircraft would attain certain speed and then missiles are launched. So in those cases, missiles can be either ramjet or scramjet type of engines, which are air breathing engines, and aircraft has attained supersonic velocity, so that we can have combustion either subsonic or supersonic with aircraft, with missiles having air as the oxidizer. But missiles can also be the non-air breathing engines like rocket engines, where you don't need aircraft, you can have missiles operating from the surface, where rockets will take the missile and then they will have their own propulsion system of rocket to be operated for the missile. I have answered the question, what is the difference between afterburner and reheater? The answer is simple, where reheater is placed between two turbines, high pressure turbine and low pressure turbine. Between two turbines reheater is placed. So reheater has the gas which is coming from the high pressure turbine, and then that will be heated at constant pressure, and then the gas will go to the low pressure turbine. So this is the operation of reheater. But in case of afterburner, there is no turbine which is there downstream of the afterburner. Afterburner is used in aircraft engines mainly. Reheater can be used in aircraft engine, but it can also be thought that afterburner cannot be thought for electricity generation. Since afterburner is mainly for propulsion system, addition of heat increases the kinetic energy, and then that is why afterburner is placed before the nozzle. There is no turbine downstream of the afterburner. पहला स्लाइड ऑन रखिए. कोई सवाल आएगा तो हम जवाब देंगे, कोई सवाल आएगा तो जवाब देंगे, अदरवाइज स्क्रीन पे स्लाइड रहेगा. Question is, what determines the maximum temperature in real turbojet engine? Maximum temperature will be defined by material constraints. Maximum temperature will be felt in the two components, one is combustor and other is the high pressure turbine early stage. So, turbine inlet will face the high temperature. There is not much problem with combustor, but the turbine is a rotating part, and the rotating part undergoes a stress strain cycle. In that, if you have very high temperature T3, then the strength gets reduced and then there is a chance of failure. So, that is why we have to choose temperature T3 based upon the choice of turbine materials. In general, as what we see, it varies from 700-800 degrees Celsius to around 1100 to 1200 degree Celsius. However, maximum temperature can be further raised if we can incorporate turbine cooling, as what we have discussed in the next part of the course. So, turbine temperature is depending upon now two facts, one is material constraint and other is our potential to incorporate turbine cooling. If turbine can be sufficiently cooled, then we can raise the temperature of the cycle, which is maximum temperature of the cycle, which is T3. Question is, in general, what will be the number of stages of compressor and turbines in an aircraft? This is a good question. We have to understand one point over here. Our aircraft, all these things are done by reverse calculation. Initially, we should think that what is the expected speed of an aircraft, what is the altitude of flight of the aircraft, and what is the payload of an aircraft. Based upon that, we can design the turbojet engine. However, we can keep one more thing in mind, that I will tell some rough numbers, very first understanding of ours, which can implement here, and we can see that compressors will always have more number of stages than the turbine. First thing is, compressor, as I said, is the machine which experiences adverse pressure gradient. At the inlet we have low pressure and at the outlet we have high pressure. So, it is an adverse pressure gradient. So, there is a chance of flow separation. So, pressure rise will take place, but that pressure rise should take place in a gradual manner. So there will be many number of stages of the compressor. They will be 8, 10, 12, and new compressors will have more than that. That is what the general compressor stages. And as what we know, axial compressor, one stage would have general pressure rise of around 1.2 to 1.4. So if we want pressure ratio of 8 or 10, then accordingly we would have many number of stages. However, if we see now turbine, then in case of turbine, turbine experiences favorable pressure gradient. That means turbine inlet has high pressure and outlet has low pressure. So turbine has not problem of separation. So we can have less number of stages in the turbine. So turbine would have stages 2 or 3 in number. Since 2 or 3 stages are sufficient to have given pressure ratio to operate, which is 7 or 8. So we have less number of stages for compressor, we have less number of stages for turbine, many number of stages for compressor. So new compressors will have many stages like 15, 16, and in general compressor stages are 8, 10, 12, and turbine will have very less number of stages, 2 to 3. If there are no questions, we would like to stop here. However, I would like to give best of luck to all students for all your endeavors apart from this course as well. Do well in your life. Thank you very much for attending this course and live session. Thanks.